Hi, my name is Aaron Olivares. I'd like to welcome you to the OpenCPI System Support Project Workshop. Today we'll be learning how to enable new platforms on OpenCPI. I'm glad you guys are here. Just a couple of things before we begin. I hope you had a chance to run through the workshop requirements page that we have on setting up your environment to follow along this workshop. In addition to that, there's a cheat sheet which you can find in the shared notes. And this is going to be recorded as well. Just a second, I have to start the recording here. Select the record button again later. Anyhow, so there are some differences if you're watching the recording. Those being that the live participants have access to a Pluto SDR over a VPN, and the Pluto SDR is functioning as a standalone in a USB host, meaning it's attached to a network interface card, and you have access through it through our network infrastructure. In addition to that, the Docker container points to an NFS mount that contains the Xilinx tools, Vivado, and Vitus tools that we'll be using today. If you're watching the recording, you would have to install those tools locally on your system under opt Xilinx. And then when you're launching the Docker container, update the volume argument with pointing to those locally as well. These instructions will be updated. I was trying to show within the workshop communicating with the local one, but I ran into issues in the previous one, so I'm not going to do that right now. But keep that's if you get we're going to update the cheat sheet with instructions on how to do so if you're watching the recording. And if you have questions while watching the recording, go ahead and email us at our discussion list so we can help you troubleshoot to get through this. So the agenda for the workshop today, we're going to 2, 3, 4, 5, 6. We're going to verify our Docker container, and we can confirm that we were talking to the Plutos over the VPN network. We're going to have an overview of OpenCPI, and then we're going straight into what it takes to enable a new system, and that includes, depending on the system, if there's an FPGA you want to enable or a general purpose processor that you want to enable. So the main goal and objective of the workshop is to create an FPGA platform and test that new platform on the Pluto SDR. Along the way, I would like everyone to become more familiar with OpenCPI and the system support project development and the development in general, and empower you to create and collaborate and share new OpenCPI system support projects. And I'll also use the chat. I'll be looking at the chat for questions and comments as well. Beatles M, there's a little cryptic there, just a bunch of numbers. And there's also a support team if you run into issues following along. So OpenCPI stands for Open Component Portability Infrastructure. And it's a component-based framework similar to blocks in GNU Radio. But one of the main differences is that components can have multiple implementations, what we call workers. An example of that, and an example that I'll continue using throughout the overview, is of a fur filter component. We have the RCC, which stands for Resource Constrained C, authoring model, which executes on general purpose processors. And then we have VHDL or HDL platforms that execute FPGA implementations of that worker. And you can have multiple of those for those author models as well. And OpenCPI is capable of supporting other compute or data engines, and we have preliminary support for OpenCL GPUs, and we have plans on continuing development in that, so we can have GPUs, CPUs, and FPGAs all in one. And that's what one of the main features of OpenCPI is, that it encompasses the entire system, and not just one particular execution. And that's what we want to bring to the GNU Radio community, is the ability to run applications across the entire system. So another thing is that we span across vendors. So we're vendor neutral, and also that includes FPGA vendors or integrated circuit vendors. And then the device workers that we generate has the capability of working on multiple platforms. And that's the whole the point of OpenCPI is the hardware agility, the ability to move this application from one platform to the other without having to start from scratch. So there's 3 distinct development processes. And today we're talking about platform development. And there's another workshop yesterday and the day before yesterday, in which you can find videos for that talk about the application development and the GNU Radio Companion integration. If we have time at the end of this workshop, I can bring it up and to show you just a little preview of that. And the other is the component. So the component development creates the libraries for application developers. So you combine the components and the platforms, and then you develop an application, and you run that application and deploy it across several different platforms. Okay, so let's start by verifying our workshop environment that we're going to be using to validate that our platform that we created works on that platform. So I'm going to pull up my virtual machine. It's on a clean slate. And also pull up your cheat sheet, and we'll start from there. So really, all you need to start, is from here to here is all that you would need, the highlighted portions. The other environment variables. So OpenCPI is a key command line. The main interface to OpenCPI is through the command line, using command line utilities, part of OpenCPI, and to modify the runtime environment characteristics of those executables, we use environment variables. The first command line utility we're going to use is OCPI remote, and that's going to load OpenCPI on the Pluto SDR. So the Pluto SDR is basically, this firmware has been is fresh, and there's no modifications to the firmware that Analog Devices provides. You can use the firmware as long as you're running version 0.32. And what OCPI remote does is it's going to load all the executables that have been cross-compiled for that embedded target, as well as any libraries and artifacts that are required for OpenCPI to run. So I'm going to start my Docker container. I just had a script with the same command that you were given in the workshop environment. This is the output that you would see when you first started, if you have not already started. Now I'm going to export the first one, OCPI server addresses. So this is going to point to the Pluto IP address that was given to you when you requested VPN credentials. Server addresses equals 192. Oh, I'm not doing that one anymore. Mine, I'm going to use the last octet is 119. Please use the one that was provided to you. And then specifying the port 12345. And then I'm going to OCPI remote. Since I just got out of the previous workshop, I'm going to use reload because there's a sandbox that contains all that files, and it's going to delete that directory and then load it with a brand new one. You would use just load. But if you get an error, because we just got out of the previous workshop, use reload, and it'll do that. The error would be the sandbox already exists. Pluto SDR 032 Pluto SDR log. So what these arguments mean. So the -s stands for the software platform. So that's the name given by OpenCPI to the software platform. And then -w is for the hardware platform. And P is because that's the password to SSH into the Pluto SDR. So it's going to prepare a server package and it's going to send it over via SSH. And this is the same type of information that you should see on your screen. Okay, server package sent successfully on my end. It can take a little while for you because I'm literally on the same network, so it's quicker for me. There was one environment variable I'd like to add that wasn't in the latest image. If you have the latest image, is the export OCPI _ HDL simulator, and this letting OpenCPI know that XSIM, which is a simulator bundled with Vivado to do FPGA simulations, is on the is available, and it doesn't have to discover it, because if it goes to discover it when we run OCPI run, it can take a couple minutes on your guys' end, and that's a good environment variable during this workshop because it'll save a lot of time bypassing that discovery. So I do I haven't started yet. OCPI remote start -b. That argument variable is to denote, let the embedded target know that we're interested in loading a OpenCPI default bitstream, because right now it's analogs bitstream. And that bitstream is used during the discovery of containers, and it's required to be there, or else the FPGA platform won't be recognized. So P analog with password. So it's going to say loading bitstream, and then it's going to spit out basically the discovery that happened on the embedded device. So we're using this in a remote container sense. So this is the information. So the container is offered to the client. You should see Pluto SDR. So by the end of this workshop, we're going to replace that platform with a platform that we generate during this workshop. And it's going to say my _ Pluto SDR. So I'm using the one that's part of the OpenCPI system support project that's located on GitLab repo. And then the driver, there's a kernel driver that gets built within an OpenCPI that handles a lot of the functions within the CPU. It does things like loading the bitstream, pinning down memory, making it available for user space, and it's basically our Swiss Army knife in OpenCPI. And that kernel driver runs from the embedded target, as well as any platform that's doing execution, and that can be the development host as well. And kind of the last things that it prints out is OCPI serve. So that's a executable that runs on the target that is opening up a port and listening for commands from OpenCPI, and that OpenCPI that it can accept data streams and applications to run. And that's what OCPI run does. When you do the -c, it's going to query all the available containers. And you should see that your Pluto SDR is available in both the FPGA and the ARM processor. And you'll see that the XSIM is available here as well as the Ubuntu 18.04 container. So there's 4 containers that we have access to. So if you guys are following along, let me know if you got to this step and we can proceed. Just gonna give a couple minute pause otherwise. And if you run into issues, again, use the chat, and under shared notes is our technical support room that we have people available if you run into issues. All right. Let's begin with the OpenCPI overview. So part of creating a project is the project organization. So each of the projects under OpenCPI projects have the same directory structure. And then based on the type of development role, and today is platform development. So under HDL, and then platform is where a lot of our source files are going to be located. If you were looking for components, there's a component directory and there's the component specification. We'll go through some more of these terminologies right after this slide, and then applications. There are several projects that are part of the source, and the core project contains everything that the bare minimum for OpenCPI to function. And then assets is the project where we store a lot of our components dealing with the software-defined radios, like DSP components, comms components, util components. They have primitives there as well. The platform project houses our device workers that handle the transceiver data and configuration device workers for those as well. And under OSPS is where we have the system support projects located. So the component in OpenCPI is OpenCPI is XML driven, so there's going to be XML document for pretty much every element, and it's described by OpenCPI component specification, and the component specification is a contract. There's no implementation behind it. You specify its inputs and the outputs and any of the configurable parameters or properties on that for the component. So the input port, the output ports is what we call the data plane, and the control is the control plane. The example would be the FIR filter. Some of the control properties, you can modify the coefficients, the number of taps, and the coefficients of those taps using the control plane. There's sometimes a parameter is a build time property. So that would be a build time example of the FIR filter would be the bit width of the coefficients, whether they're 16, 12-bit, or the bit width of the coefficients themselves, or the data widths of the ports as well. So the implementation is called the worker, and you can have multiple ones, and there's different types of authoring models, the RCC, HDL, there's OCL for the different types of authoring models. Within the worker, there's the source files. That includes a make file, a dash build XML that you can change the different the parameters of that component using the parameters specified in the component specification in that file, and then the source file, and that would be a C++ file or VHDL file. And the outputs when you use the OCPI dev command to build it on the RCC side, in all of the authoring models, you'll generate an artifact, and that artifact is a binary file that contains in the RCC sense it contains a shared object, and then the VHDL would be in the workers stage would be an edef netlist, because we use incremental compilation with our FPGA development. So once we have our components and workers, and the communication, the messaging between those components is defined under a protocol specification XML. This example, because we're in the SD software-defined radio realm, is the real and imaginary data types, and this is a timestamp. So we use operation what are called opcodes, and the operation time is 64-bit time that has a timestamp. So we have our workers protocols. We start stringing them together and create an application, and the application is an XML document called the application specification XML. And this is this is an example of a simple application where we instance those components and then we connect them. So when you instance them, you can specify the component, just the component name, and it will look in the library of artifacts and find the workers associated with that component, and will automatically, if not told to do so, will automatically execute from that library. There's a functionality that allows you to be more specific if you want, and you can move that. If you had the fur filter, for example, has both authoring models of HDL and RCC, you can move that functionality freely within the application when you execute the application. So you can have the fur running on the CPU, and you might notice that the fur's execution is being a hog on the processor. You need to free it up, so you can move it onto the FPGA without having to write any more source code to do that. To do that, you would create we'll go into that in an assembly. Make sure there's an assembly with that in there. So a platform is a physical motherboard housing one or more interconnected processors and associated I/O devices. And we'll be using the Pluto SDR as an example. In that, the Pluto SDR uses the FPGA from the 7000 series Zinc, and the Zinc has embedded inside the same chip hardcore ARM processor and the FPGA fabric. And the interconnect between the fabric and the ARM is through OpenCPI is through the AXI ports. There's two types of AXI ports. There's the general purpose and the high performance ports. Before we get into that, though, the container is the OpenCPI execution environment on some platform that will execute workers. So on the general purpose processor, the RCC container, this is where the worker is going to be executed. And then for GPPs, you can have multiple containers within the same platform, and that could be like have a container per core of the ARM processor. So in the Zinc 7010 has a dual core ARM, so you can have two containers, and OpenCPI will facilitate the data transfer between those containers. So those two cores using shared memory. And then the FPGA side has its own container. And it's the job of the platform worker, the platform developer, to enable the execution of those workers on there. And there's several layers within the container on the FPGA side that are needed to accomplish this. The first one is an HDL assembly. An HDL assembly is a set of workers that are connected, similar to an application, but except. So the whole point of having this HDL assembly description XML is so that application developers don't have to worry about the nuts and bolts of the rest of the container and make the FPGA work. They just focus on the application. So the assembly houses just all those workers and how those workers are connected and connected. So the jobs of a platform HDL platform developer is creating device workers. And we have a set of device workers that handle the communication between the transceiver and the FPGA. And those device workers are created in the container. And there's the HDL worker XML. It's a special type of worker, so it uses the same worker XML. But there's also a cards and slots paradigm that enables an FPGA developer to, in the instances that your platform has a slot, the Pluto SDR does not, but others that have like FMC slots or other types of mezzanine connectors, there's XML documents that allow you to specify that slots inputs and outputs, and that's the device worker has the ability to talk to FPGA I/O directly, because you need to in order to talk to other integrated circuits on the same PCB. So you have the card itself will need device workers on that card, and we have XML that handles that configuration, so that you can have that platform have containers with and without those cards on there, and switch out functionality easily using those XML documents. So what we'll be building today is the platform worker, and the platform worker is the worker that that instantiates the the processing system, instantiates the interconnect between the containers. Whether it be, in our example, would be the AXI, but we also support PCI Express. We have support for Ethernet as well. And the platform worker handles the clocks and the resets, all the FPGA processes to get that platform running, and that containers data, both data plane and control plane, communicating to other containers. So we talked about the control plane. It flows through the platform worker, and the control plane again is the configuration of runtime parameters of the worker, and the worker also has a life cycle. So there's a start, executing, and a stop, running type of life cycle that are also queryable, and that includes the workers of the assembly, everything, basically all the workers inside the container, and then the data plane. And the data plane we use, the container data engine we use is called the SDP, meaning scalable data plane. And the scalable part of the name is to denote that the data plane can be it supports multiple bit widths from 32 bits all the way to 128 bits. And that also flows through the platform worker, and we'll see that soon. Okay, so platform development is really based on the platform you're trying to enable. If it's just a processor, or you want to enable the RISC-V architecture, you focus on the software platform development. We'll get into that. And the FPGA platform, there's the enabling of the FPGA itself, and then there's the enabling of the device types, or the device for the specific integrated circuits. It'd be like a clock generator or EEPROM memory that communicates over SPI or I2C, things like that. And those device types, unfortunately, we don't have time to go more into development of that today. But the idea is for it to be like Linux drivers that we implemented once in the FPGA, and then we can just reuse it across all supported platforms. And then for software development, there's the task of enabling a development host. And examples of that would be enabling another flavor of Linux, your favorite flavor of Linux, and then or the target platforms, and that entails cross-compiling for that target. OpenCPI supported platform list. We support the RCC platforms. So we use the toolchain and the Linux kernels provided by the Xilinx vendor. And those tools are updated periodically by quarter and by year. So that's what the 19 stands for, 2019. And the 2 is the second quarter, the second deployment of that set of tools. You'll notice the difference for the Pluto is we use the software, the kernel version provided by Analog Devices, so that we can maintain, because it doesn't use an SD card, and we can maintain all of the nice features of the USB device, whether it's the host or if the Pluto is acting as a device, which will enumerate the serial port, the Ethernet, and the mass storage device that allows you to update the firmware. So HDL platforms, the Z, and the Z with the FM comms transceiver, the 9361, E310, the Zinc UltraScale, Pluto SDR, Matchstick, ML605, and ALSD4. We're in active development for various other platforms, and I'll share with those towards the end of this presentation. And then other platforms that are considered FPGA platforms are the simulators. And we support iSIM, which is bundled with ISC, Vivado, which is bundled with, XSIM, which is bundled with Vivado, and ModelSim, which is a third-party HDL Verilog simulator. So enabling a new system. What are the steps to do so? So the first step would be a system inventory, which elements are relevant of the platform that you want to enable with OpenCPI. Second would be assessment. What is the current level of support that the framework provides? Is there additional pieces that are missing that I need to develop? And then additional system information of the platform. Those being the data sheets, schematics, constraints files for FPGAs. And then if some of those things are missing to complete the project, then you would have to experiment and fill up those knowledge gaps. Using the Pluto as an example, so the number of processors, processing elements, there's the dual core ARM and the FPGA fabric. The interconnect would be the AXI bus that communicates between the fabric and the FPGA. The FPGA and the ARM. And then the one device that we want to enable is the transceiver, which uses the CMOS data path and configures over SPI. Assessment of the current level of support. The Zinc processing system was already supported within OpenCPI at the time of enabling Pluto SDR. With a slight difference, the Zinc 7010 is a smaller chip, and the DDR memory only supports 16 bits versus 32 bits. So there had to be a modification to OpenCPI's core or framework to enable this to happen. And when you guys in Prop come across the same similar situations, we encourage you to create merge requests within GitLab, and so we can continue to increase our capability across different types of architectures. And then the interconnects, we use 2 IP cores that are part of the core projects, is the XC to STP and the XC to control plane. And there's currently support, we currently at the time supported the 809361, and the 809363 matches all the registers and the data interfaces exactly, so that was reusable. Gathering information. Analog Devices does a really good job of providing all their data sheets, reference designs, schematics, clocking information. Their reference designs include all that information, as well as how to debug it if you need JTAG access or UART serial access. And then any knowledge gaps. Again, for the Pluto, it was well documented, but sometimes not information is available, so you might have to reverse engineer some things to get things working. So FPGA platform development. Let's begin working on our platform worker. So before we do that, it's just important to note that you have access to the tools. Your development environment contains everything that you need. So the platform worker will require Vivado 2019.2. And then the execution, we need to make sure that the VHDL file contains all the IP cores that we need to instantiate to facilitate both the control plane and the data plane. So this is a block diagram of the cores that are implemented inside the FPGA for a Zinc processor. And you can use these same steps to go over to enable any Zinc FPGA based processor. And I don't know about you, but I am an FPGA hoarder, and I always I always purchase new FPGAs. I have a laundry list of platforms that I want to enable, like the Ultra 96 or the Snickerdoodle and other FPGAs that have the Zinc on it. Following the steps, you can quickly enable those platforms as well. So part of the platform worker, which we're going to build, has the wrapper. OpenCPI has a wrapper around the Xilinx primitive. And then those IP cores that facilitate the control plane and the data plane. There's 4 high-performance ports. That's what this CX stands for. So, and you have the option to only use one, or use all 4, or use anything in between. There's another optional XML document called the platform configuration, and this is optional, and but it allows you to enable or disable specific device workers. If you had a device worker that was very resource intensive, and you wanted a particular bit stream that didn't have that one to free up resources for the assembly, you have that capability as well. So OpenCPI has the ability to synchronize with GPS time, and has a time server that facilitates timestamping of samples from the ADC or the DAC, or from the ADC really. And then there's the time client that feeds the device workers that run in the clock domains of the transceiver itself. Then we have the HDL assembly, where it has the workers that are actually executing. One thing I want to note is there's a read-only memory that contains UID and metadata to identify what bitstream is currently loaded, and that's queryable from the ARM side. So you can see what exactly is loaded on the GA fabric. So we move on to our workshop cheat sheet. We can start creating our HDL platform, and I'm going to do it as well together so I can explain the process and specific files and modifications. So the first thing we're going to do is we're going to create an OpenCPI project, and we're going to put that project inside of the OSPS directory. So I'm going to go under OpenCPI projects OSPS. You'll notice that there's load SDRs there already, but I'm going to use the OCPI dev command line utility to create this project. OSP GRCon 2020. So what that did is we're going to see change directory into that project. I created a make file and the project's exports. So the project's exports, so there will be multiple projects in an OpenCPI environment, and the exports denotes that there's certain files, whether it be components or HDL platforms, that need to be exported so that other projects have access to those, and vice versa, to have access from build source files from other projects as well. So the first thing we're going to do is we're going to depend on the assets project. To do so, according to the cheat sheet, we're going to just create the HDL platform first, and then we're going to go OCPI dev. Inside the GRCon 2020 project, we're going to create HDL platform my OSDR. And then before we go into there, we are going to update the project.mk file and let the project OpenCPI know that we want assets from assets project. These other directives here are for namespacing and naming. So I'm going to call it OSP GRCon 2020, and these match the directory's name as well. So the name is OSP GRCon 2020, and the package prefix equals GR. And this is the project dependency. It would be safer to copy and paste it. Dependencies equals OCPI assets. I'm going to say that. And then please feel free to use the editor of your choice. I'm using Vim, but if it's not available in the Docker container, just have to install it to get things going. So once we got the project.mk modified, we can drill into our platform directory. So under HDL, this is what OCPI dev created, our platform. And it has a make file, .mk file, and the an XML file. And XML is the worker description XML. So an HDL platform is based off a very specific component specification. and that's denoted in the XML automatically when we generated that project. Let's go. So we've changed directory, and now we're under FPGA project. So part of building any artifacts using this platform, we need to let Vivado know what FPGA part we are building for. So we're going to open up my Pluto str.mk file. And we're going to update it. By default, this is 7020. We're going to update it to 7010 and to make sure that the part number is 225. And yeah. So the next step, we're going to modify my Pluto.xml, the worker. And the first thing we're going to modify is we're going to make it version 2. And version 2 within the framework has additional abilities in the way we reference libraries in VHDL that we want to enable by specifying that. Version equals 2 up here on the first XML line 2. And then within the same file, we're going to remove and delete line 7 because we're going to replace it with this block of XML attributes. Okay, and then I'm going to go over what each one means. So part of the XML is going to use OCPI gen to generate the VHDL files that are going to be used to generate the workers netlist that will eventually be used to generate the bitstream. And the scalable data plane is what we use for the data plane to communicate with the workers, the container data engine, and the other containers. And we want to make this platform worker the master and the count to have 4 of them. And that corresponds to the available number of AXI ports. And you could change that here. The next thing is some just debug properties. Whether AXI errored out is a boolean true or false, that would be queryable. And then the STP drop count, the number of dropped STP messages. And then the control plane, we're letting the OpenCPI know when it goes through its generation that this is going to be the master. And then the use GP1 is a boolean, and if it's true, this is just a way to allow us to test both general purpose ports on the AXI bus to move the control plane from 0 to 1 or have it at 0. So some of the other XML in here is the time server. We need to let it know the frequency of that clock that we're providing the time server, and it's 100 megahertz clock. And then this is the name of our platform, my Pluto SDR. So we've got that. So at this point, if you were doing this without a reference, you can do an OCPI dep build. And this is going to go generate some VHDL for definitions, or it's going to make a skeleton VHDL file, and as well as an implementation based off that XML that we modified. But we can Control C right after this. If we let it go, it'd take about 10 minutes. It will finish, but there's nothing implemented in the VHDL. Because let me open up an LS here. You'll notice that it generated a couple more directories, and it generated a skeleton VHDL file. So this is what the skeleton looks like, and it has some of those properties from the component specification, the defaults. And there's just standard things like LEDs and switches that you would normally see on a development board, FPGA platform develop. So the next step within our component data sheet, our cheat sheet, is we're going to take some information from the currently supported one and bring it over here and change some names, and I'll review and we'll modify them together as well, in the interest of saving time versus typing everything from scratch. just copy and paste that into my Docker window. The first one we're going to review and modify is the exports. So just like in the platform level, there's an exports file. There's one in the project level. There's an exports file. There's one in the platform level. My project.exports. So what this is we're letting this. So what we're doing in the platform also is these things are going to go to the project level. But there's 3 different types of exports. There's deployment files. Those are denoted by the first character, and that's a plus sign. And the equals is a runtime files. So required by the runtime executables, these files. So we're exporting that. So it's available outside of this project. And then there's deployment files. The ones we're going to modify here is the development files. So when you're building the bitstream, you would need a constraints file, and that's what these are, constraints files. And when building an FPGA platform, we try to use the constraints file provided by the particular manufacturer of that platform, or if it's like a development board and such, and try to keep the same namings that they use for the pin assignments and signals. So we made those modifications. Just double checking. The next file we're going to modify and review is the system XML. So when running OpenCPI, it looks at this an XML. It's called system XML, and it gives it information of how to load OpenCPI and what modules to load that facilitate transfer data between containers. This being a Zinc platform, there's 2 containers. Again, you can have multiple of one container type of RCC, but we only instance one RCC container in here. So one RCC and then one HDL, and then the device. The PL stands for programmable logic, and the platform that we want to name this, because we're creating a new platform worker or a new platform called My Pluto SDR. So the transfer modules here. So PIO is for shared memory. We have containers with access to shared memory. We'll utilize that. Socket module is for remote containers, communicating. So from the host to the embedded target, like we've shown with OCPI run, that uses sockets. And then DMA is used for transferring of data between the FPGA and that's where the AXI is implemented, is through the direct memory access from the ARM side. The next thing we're going to modify is we're going to open up the make file, and we're going to let it know that we're interested in using libraries part of the core project. So we did add the assets project, but core is automatically accessible from any project without any specifying in any of the project files. So vim make file. And we're going to add libraries, and these Zinc is for the Zinc processing system wrapper located in core. AXI is for our interconnect, and SDP is for the communication between workers and the interconnect. Make that modification, save it. So at this point, we're ready to build our platform worker. So because we did a build earlier, some of the generation files are stale now. So I'm going to do an OCPI dev clean and then OCPI dev build. Oh, fat fingered. And the reason that we're building here is so that if there are any mistakes that we've done in the previous steps, we're automatically going to see those changes. It's gonna kick back and an error out. Normally, at this point, you would be able to, if we had all the time, would be able to do OCPI admin install platform after registering the platform. But we're gonna let this platform worker build for a little bit, and while it's doing that, I'm gonna review the steps of enabling a general purpose processor. It took me about, I think 10 minutes last time to get this built. And what it's building is the netlist that is going to be used for when we compile a bitstream, because we use incremental compilation. We're just building the platform worker for the Zinc target. So target is a new term that I didn't mention before, but target is basically the architecture of the FPGA, or FPGA architecture, or not just FPGAs, but also like CPU architecture as well could be a target. So if you build, and this is to save time on building all the components or assemblies, that if they're not assemblies, just components, that if they're built for the target, then they're shareable between platforms. So just to be reusable. Okay, so the next step I'm going to do is I'm going to open up a new terminal, and I'm going to use that terminal to discuss the general purpose process. Now, hopefully, if we have people following along, let me know in the chat how things are going. If you've been able to follow along and start the build as well, it'd be helpful. Thank you. So software platform development. There's two. There's the development host and the target host, or target platform. The steps for that, it's very important that all steps should be recorded for reproducibility. First step is to install the options and packages needed to build the OpenCPI's source code. And I'll show you a file where you can use as a reference, depending on, and we utilize the package manager available of the operating system to facilitate the installation of OpenCPI. And also to one of the packages, it's very important because we have to build our loadable kernel module, kernel driver, is the Linux kernel headers, and that's one of the benefits of development hosts, is that the headers are available in a package that we could easily reference. The next step is to make sure that the tools that we need for the platforms we want to support are supported natively by that operating system. Those tools, if you wanted to target a Xilinx FPGA, would be Vivado and Vitis. So that operating system would have to support those. The next would be to retrieve the source code to build against it. So the following steps are the same for the target devices as well, and that would be building the kernel driver and then building the environment and the runtime executables that we've been using to work on that particular platform, and then to build the component libraries that are available in OpenCPI to run those example and the example applications. So, like I said, I'm going to go and show you guys what those things look like. Mine finished really quickly. So my platform workers is completed, and I'm going to go ahead and issue the next command of the cheat sheet, which is the OCPI admin install platform. Is register the project. So like I said, so far we've created a project, we've created a platform, and we've created the platform worker that's going to run on that platform. And to query the registered projects, CPI dev go registry. So these are the ones that OpenCPI is currently aware of. So we need to make OpenCPI aware of the GRCon 2020 project. To do that, there's an OCPI dev register project command that we can register this project. And I probably mistyped something. GRCon. Let's see what says is not a project or does not exist. Oh, I went too far. Uh, okay, so we do OCPI show registry again. I just copied and pasted the cheat sheet. I just drilled down all the way to platforming, and that's not a project. That's a platform. OCPI dev show registry. There we go. It now is aware. So the next command we're going to use as part of the framework is OCPI admin. And there's two functions. There's the install platform and the deploy platform. And we're going to use the first one, which is install platform. my_pluto_str. So what is going to happen is it's going to look at all the projects that are registered, and it's going to go through the components and make sure that there are any HDL, because this is an HDL platform. It's going to look for HDL components, workers that are implemented and make sure that they're already built. And since they've already been built for the target sync, because they've been built for the Pluto, the standard, the one that's in the repository, Pluto SDR, it's going to go through these fairly quickly. One of the last steps it does is it builds a brand new bit stream, and it builds the test biased assembly, which includes one component, and it takes data in, and then the bias, it just adds a value to that particular 64-bit data, and then it shoots it back out. So it's doing hardware acceleration, and that's basically our default bit stream that we use, and it's our hello world that we use within OpenCPI. So if you got in there, and this part takes a while because it's going to build a bit stream, and we will return back to investigating the enabling of a development host in a new window. So I'm going to open up a new window to my container environment, the Docker container. I'm going, and to do so, I need the container ID. So I'm just listing the containers we're running. Docker exec. So I'm running I'm in the same container, just in another terminal window. And I'm going to go to OpenCPI. So the software platforms stored under projects core, RCC, the core projects. And under, see, if you notice that the same directory structure for every project, similar, RCC, platforms. So here are all the software platforms inside the core project. And this includes both development hosts and embedded targets. So you'll notice there's CentOS 7, CentOS 8. We're just waiting on the tools right now to catch up to CentOS 8, so that would be a fully operational platform soon. Mac OS, again with the tools, the Xilinx or Intel's tools don't work natively in that operating system, but you can run RCC containers, and you could build RCC workers in the Mac OS operating system. And then the operating system that we're using now is Ubuntu, and the Ubuntu 18.04 is what we're running, and we also support 16.04. The tools work on both 16.04 and 18.04. So let's look at Ubuntu 18.04 as an example. There are 4 files. So part of installing from source code, we have a script called install OpenCPI. And one of the first things that script does is tries to detect what platform it's building on. And to facilitate that check, there's this -check.script, sh shell script. We'll look into, and this is operating system dependent, so it's different for every operating system. But for Ubuntu, there's a file under etc called lsb release, and we use that to tell the difference between 16.04 and 18.04. So the distribution ID in that file is 18 or 16, and then the release is the 04 portion. And if it matches to 18.04, then it's going to build OpenCPI for that platform, for 18.04. So this is the hyphen packages is where you use the systems package manager to download the correct packages required to build OpenCPI. So this is a good reference in the list that you can use. Sometimes the different package managers use different naming schemes. So you just have to match those if you're enabling one that currently isn't. Ubuntu uses apt and CentOS uses yum. And they're organized by function. So for runtime minimal, if you wanted to just execute things or execute artifacts, you only need this. But if you wanted to build the components, the workers, you use these other packages as well. Then towards the bottom is where we call the apt installation. The next file that I want to highlight is the .mk files. Again, with the development host, the nice thing is that we have the ability to get the kernel headers from the package manager. And this is where how we point to OpenCPI to find those headers using this make function. We know where they are at. Look, you would know where they're at located, and you can find the headers. And this is how you point to OpenCPI to when it runs the build for the kernel driver, it knows where to find them. And that's about it for a development host. Let's see. So general purpose practice platforms are similar with the change that we're cross compiling now. To do so, we don't have the compiler. The compiler is part of a tool chain, and we have to acquire that tool chain. And for the example platforms that we have, we use the Xilinx tool chain that's provided in their installation. 2019 twos, their tools are called Vitis now. It used to be called SDK. Once you have that, we can cross-compile our runtime libraries and the executables, the command line utilities, and the kernel driver using those tools. But we have to go and acquire the kernel headers, and it's not as simple as a package install for those. So yeah, where is it coming from? And it again, OpenCPI is very flexible in the sense that you don't have to use Xilinx tool chain. You don't have to use Intel's EDS tool chain. You could use any tool chain that you need to use for that particular architecture platform that you're trying to enable. So I'm going to show you what the Pluto SDR software platform looks like, and kind of the same steps that you have to do when you don't have access to kernel headers. And essentially, we use the tools to compile the kernel in its entirety. And once the tools have been compiled, there's a script that we've been using. It works fairly well to extract just the headers and then make those available using the exports at the platform level, and export that from and accessible from OpenCPI when you use the OCPI admin install platform. So the Pluto's platform is located under OpenCPI projects, and the OSPS, OCPI, Pluto SDR. And in there, it's the same directory structure as the core and as the one we've created. So platforms, there's only one. And again, we're using the kernel that's provided by Analog Devices so that we can maintain that functionality of the USB port and its flexibility of acting as a device or acting as a host. So under ADI, Pluto SDR. You'll notice some differences. There's a scripts directory, there's a make file. And in that make file, we use that make to execute those scripts. And the scripts, there's one script that just does a git clone of the repository, and then it checks out the specific version of this platform, which is version 0.32. The way that the analog devices, they use Git sub modules. So that sub modules has a very specific commit tag, commit that from the analog devices kernel, and we use that we build against that because that's the exact same kernel that's running the stock SDR firmware. And once we've built using the tools, there's another file that points to the tools, which I'll show you. So here's the script to source it. Here's to create it. And so the runtime executables have a SDK that need additional libraries because they're C++ libraries, and that's extracted from the software development kit, and that's a standard thing that we've done with the Xilinx tools. Once you get those two things running, so it's going to extract it, and then the next file that I want to highlight is the exports. They're the same as the other exports files that we've seen thus far. Plus is for development time, and we want to extract the kernel headers tar that script generated that contains those kernel headers. And then for runtime is the equal symbol. That's for the SDK libraries. Part of the tool chain has those libraries already pre-built so that we could run C++ executables on the embedded ARM platform. The next file is the .mk file, part of this platform, and this is where you pointed to the correct tool chain that you want to build against. And we're forcing it to run against the 2019 tools. So when developing for OpenCPI, you need a really large hard drive space because of us as OpenCPI, the OpenCPI team tests across many different versions of Vivado, and each of those is about 60 gigabytes of data just for their Vivado and their software development tools. But there's some directives that are part of this include that helps you find where they're located on the system. Typically, when you install using the defaults from the installer, they're under starting from 2019 I believe, is the tools/Xilinx directory. Previously was opt/Xilinx, and in your Docker container, that's where they're at right now, Xilinx. But this will find the correct directory, and then inside that directory, this is where you find the compilers. There's this is the kernel headers and the directory where to find them. The ARM, this is the cross compiler directive that uses, so we're going to use GCC. And then the architecture is 32 bits for the Zinc processor. And that is for an example of the general purpose processor using the Xilinx tools. So we also have a set of scripts that help you generate the Xilinx versions, and so you can generate any version in between. By default, we have in 2017.1, 2019.2, and 2013.4 in our core projects. But if you needed one in between, because there's already been a lot of development, and you're stuck at a particular version of the Xilinx tools, and then we have scripts that can create the RCC platform with basically just one line, just specifying what version you want. You obviously have to. There's some steps you have to make, and in our documentation, we have steps that you have to do, like cloning the Xilinx kernel tree, and then also installing the pre-built binaries for the boot.bin that contains the first H loader and all those things that execute the Zinc on startup. So I'm going to switch back to my other window and see if it's progressed. You'll notice here this output is from Vivado, and it's already gone through the optimization stage, the place, the route, and the timing, and it's on its final legs of generating a bit stream with our new platform that we created within this workshop. So this is I am using the NFS mount too, but I'm located in the building that is being served out, so this might be a lot significantly faster for me than it is for you. So let me know if you're following along and it's still building for you. I think I've asked this a couple of times, so maybe a lot of you are just observers. And if so, then I can proceed in the chat. It's been fairly quiet. Okay, I went to the other chat. Andrew, I think, was part of the previous workshop. So anyway, we've got our platform built. And now, since you guys, it's hard to tell if you guys are still waiting or not, or you've been following along. You might finish a little earlier. So now that it's built for me, I'm going to show you guys. So I've completed the software for embedded targets and host devices. So let's talk about what does it mean to complete a platform, and specifically a Zinc platform, because we have two types of platforms, the RCC and the HDL. So one of the first things that we do when developing a platform is going through the components and the component unit tests, executing that for every worker. For every component specification file, there's an associated unit test. And also for every component file, there's also documentation as well for every component. And then successfully tested against that in hardware. It was an RCC, just the RCC component unit test. And then the platform has to have the ability to install using the OCPI admin install platform, because that's our standard way of installing new platforms. Pluto does not have an SD card, but for those platforms that do, OCPI admin deploy platform combines both the software platform and the hardware platform and generates a directory with all the files it needs to boot from that SD card. And that's nice to have as well when completing a project. And I know that's not applicable for all types of platforms, because this is, again, this is the Zinc, and it's both platforms in one. The next thing would be to test the assemblies, and specifically assemblies that pertain to devices and device workers that are implemented on that platform. The first one that I do is to test hardware acceleration is the test bias application, and that's the default one that gets built with the OCPI admin. And we had time. So if you do have one that has a transceiver on it, I mean, SDRs will have transceivers on it. There's specific tests to test the data path interface. If you have an 80 analog devices, 9361, or in that same family, we have tests that test the basically send data to the transceiver, and it digitally loops back to the ADC channel, and to validate that all the bits are coming back as expected. So there are 3 different modes that platforms are capable of running: standalone mode, network mode, and OCPI remote. And OCPI remote is what we're using now, and what you would use to do all the hardware and the loop testing of the components, the component unit test. The network mode utilizes NFS on the development host to share all the executables that have been cross-compiled for the target, and/or artifacts, and make them available, so you're not using any of the space on the embedded target, and you have access to a whole. It's good for debugging. And then standalone is that all those files are located on the platform itself and require no network connection at all. So those are the 3 modes of platform development. Let's go back to virtual machine. So since that's completed, we can proceed on to the next step in the worksheet. So we did it in the very beginning, but we did it and I was going to show, we were going to do other things while we were waiting, but it seems like waiting for others to complete as well. But I still haven't gotten feedback if others are waiting for that. So I'm going to press that. So we're going to reload the OpenCPI on the device itself. So I'm going to do OCPI remote to use our new platform that we created, -S for the software platform. Software platform has not changed, so we're going to use the same. And then the hardware platform is going to be the new one, my_Pluto SDR and -P analog. So what this is going to do is going to delete a directory, the sandbox directory. I'm going to create a new package with my new platform. And it's going to give us the same feedback we did getting. Okay, so the package is there. Now we have to start it, and make sure we have to use the OCPI remote start with the bitstream argument -B so that it could load the bitstream that we built. Analog. Okay, we've got positive feedback that it's currently running. And if you notice in the printout right here, it's loaded with our new my_Pluto SDR. So now let's run an application against it to actually utilize it. We know that it's serving there. Hopefully, I ran into troubles in the previous workshop, so I was trying to do two different things. So the application we're going to run is the test bias application, so the hello world for the platform. OpenCPI projects, assets. It's under assets. And again, if I this is the directory structure. It's exactly the same. It has a couple of a different thing. Artifacts is where go into artifacts. So these are our links to all the artifacts that are available that are in the assets project. And you'll notice that so this particular RCC worker was built for Ubuntu 1804. We have it built for the ARM on the Pluto. We have some XSIM binary bit streams that run on the simulators here. For LS, I'm going to grep for Pluto. About my Pluto. Here, so inside this artifacts directory, there's a link to the assembly that's going to run in the assembly that we need to run the bias application, test bias application. So under applications, there is the XML for that test, the application we want to run. It's called test bias.xml. So the OpenCPI application specification, OAS. In the application, there's 3 components. So this component here is the file read. We're connecting it to the bias component. And these are the properties. So this is the input file. It's metrostat granularity. This is the bias value. So 1, 2, 3, 4. And then that's connected to file write. So another OpenCPI command line utility is OCPI run. And I like to use -V for verbose and then -D for dump of the properties. And then you can specify a lot more things, and there's a man page for that for all the different options that you can use. But right now I'm just going to do test bias.xml. So I scroll up to the printout here. One of the first things it does is it detects what containers are available. So this is exactly what OCPI-C runs. So our Pluto is there. But then we actually under here, sorry about that. So this is the available containers. And this is where it actually deployed. And there's an instance of each of the components associated with their workers as well. And we'll notice here that this ran locally on the Ubuntu platform because it's using the Ubuntu artifacts. So we don't want it running on Ubuntu. We want to run it on our new platform that we created. So let's run it on our new platform. To do so, there is the -P to specify specifically what platform you want to run. And then you have the way to do this is to name the component you want, the component you want that to run on is the bias component, so the middle component of the application. And then we're going to do my_roto_str. We're going to run that. It's going to communicate over sockets. We should get and it completed. So with our platform, we were able to execute an application using. Well, let's go validate that by scrolling up to this OCPI run. Instance 0 it ran on Ubuntu. It's file read, and then instance 1 is bias, and that ran using the my_Pluto_SDR bit stream that we generated during this workshop. And this is the container it ran on. It's on PL for programmable logic, and that's the IP address of the Pluto I was using. If you were following along, we would also use the Pluto. It would show the Pluto IP address that you were assigned. So that's that application. So normally it would take a while for others, and to fill that time, I was going to go over executing unit tests and executing just a little brief overview of what the integration with GNU Radio Companion and OpenCPI, what that looks like. So for a unit test, because one of the things to complete a platform is to run against the unit tests. So what is a unit test? So under assets, components. I'm going to use a specific one, and this one was just chosen specifically because it had the smallest number of test cases. Otherwise, it would take a while to get through all of them. So under comps, you'll notice here that there are different authoring models that this component is built for. There's an HDL worker, and there is a RCC worker implementation of it. And then you'll also notice there's a test, and then there's a specs file. So we go into, I guess we could show all of it, the specs file. This is the specification. This is a specification for the worker that we're going to run unit tests against. So it has a property M. So this denotes the number. So the FSK mapper. It's a 2FSK or a 4FSK. And the symbols. And then there's an input port and an output port. That's the specification. And there's an HDL implementation that has its own worker description. And there's the build, all the elements and all the inputs that I've talked about before. But let's go into the tests, because the test is also where we place the documentation and where the document gets generated, as well as there's a function to generate the input data, and there's a Python script that does verifying of the data. And then if you wanted to view the data, in this case, I think it just does a hex step to view the data. But that has its own, a unit test has its own XML to describe it. And all that is, it'll use HDL file IO. So if you're using a simulator, it'll use a specific type of implementation to handle the file read and file write. It will not use the RCC implementation for the host platform and use the simulator version. And then input port, output port. So the input port, this is where it would generate, it will execute the Python script to generate, and then the output is where it would verify it. And as far as our documentation, you can find that at opencpi.gitlab.io. And this is for the MFK mapper. Inside, there's a data sheet for each component. And there's the worker implementation details, what exactly it does, its functionality, a block diagram, source dependencies. But this is what I wanted to show you. There's a component spec, properties, what they mean, if it's readable, it's a parameter, and then the protocol, what protocol it uses. You can find that all information there. So if we go just one more directory up, where we can see all of the different implementations, and we would run OCPI dev, run test, MFK. So it's going to go through the generation steps. And then in the first platform it chose was XSIM. So it's going to execute that test, those test cases. There's two, and those are defined, those have its own XML, like I showed earlier, but then you could also you could create any number of combinations of properties or parameters that you want to test. What I wanted to show here is that it's going to test against multiple platforms at one time. And this is what our continuous integration, continuous development does in its testing, and how using the OCPI remote, the OCPI serve executables, we can test against hardware in the loop testing. So it finished with XSIM, and now it's doing the RCC platforms. And then normally it would do the HDL platform too, but since it hasn't been built for the specific platform that we just recently generated, it's only been built for the Pluto SDR platform and not the my_Pluto. It didn't run on that, but it would run on that if it was built for it, because I'm just executing the test, and I'm not building the test and the assemblies, because the unit test framework within OpenCPI handles the generation of assemblies automatically for you. And the last thing I wanted to show was just a brief demonstration of the GNU Radio Companion integration. And to launch that from your Docker container, you just type GNU Radio Companion. The bonus. Again, if you wanted more details and a more run through of component and application development, because this is the whole point. If you enable a new platform, and then application developers have the opportunity to run their application on your platform, and that application development is done with GNU Radio Companion. So we're currently in the process of updating. This is GNU Radio Companion 3.7, and we're in the process of updating GNU Radio Companion to 3.8 and above. Right now, there's some limitations on the mixing of blocks between the GNU Radio Companion and the OpenCPI runtime environment. Right now, each flow graph is compatible with just one runtime environment, and we have a way of exporting data using sockets to the GNU Radio Companion. Again, you can watch the video about that in Jim's workshop. But in here on the top where the blocks are located, the core is the GNU Radio blocks, and the OpenCPI is the OpenCPI blocks. They follow the same structure of assets and core that they do in their directories. And what we're going to build real quick is just the test bias application. And then we're going to try to put it on different platforms. So under core, there's the file read, All right. So what it's going to do, it's going to build the same XML application file that we saw that I opened up earlier. But we've built this. We're building it using the GNU Radio companion and the bias. You connect them up just like you normally do with the GRC blocks. And then we're going to fill out these property values. These come straight from the component specification. And then there's some deployment mechanisms here as well, so we can specify exactly where we want them to be deployed. So on the cheat sheet towards the very bottom in the bonus section, we're just essentially just building the same application we ran, but using GNU Radio companion. So for the writer block, we need a way to let GNU Radio companion know that it's been completed. And there's a done attribute right here where it says OCPI done to let it know that it's successfully completed. So we're going to go ahead and save it. The GRC flow. We're saving the GRC flow graph. It hasn't built anything yet, but when you include, there's a button here. It says generate the flow graph. We'll generate the OpenCPI XML required to run this. And then after we've generated that, we can run the execute button. And it came out really fast up here. And it has the same printout that we saw with OCPI run. That's where it's getting it from. And we can see that it ran on the Ubuntu host. And then modifying those deployment mechanisms within this dialog allows you to move that application. Let's move it to the ARM processor. So execute that, and then we made a modification to the block by specifically saying OpenCPI platform, and I'm going to say the platform is the Pluto SDR32. I'm going to generate the XML again, and then re-execute. Take a bit longer because it has to go out over sockets, and then we look at the same implementation, the instancing and the deployment, and we can see that it ran the biased on the Pluto itself, the RCC platform. I'm going to give this a try, but I have no guarantees to work because the Pluto container that's executing right now is the one that we created, and we haven't regenerated the blocks to include that. But I think if I put so instead of specifying the specific platform, because it's not going to show up here, then my underscore platform, I can say just the PL of the Pluto to execute that. And it gave me an error for some reason. Oh, my Pluto is not registered. Oh, the domain key. Yeah, because I haven't regenerated it. Anyway, otherwise, if I was still waiting for the platform worker to build a lot, and the OCPI platform to install, I would have been able to show that. Yep, and it gave us the correct error on why we can't do that. Cool, didn't know that. So anyway, we showed this simple application. It could be complicated when we have an FSK application built with GRC that is our go-to example application when developing transceivers. Is a simple FSK application to send an image and receive an image. That's available in our source code as well. All right, let me return back to the presentation. So our short-term platform-specific roadmap. So the OpenCPI team, as well as third-party contributors, are trying to create more platforms, and this is just a preview of what to expect within the next year. Xilinx RF SOC support, X310, so that will include updating RL2 framing to support Ethernet frames as an interconnect. The N310, E320, and there's several transceivers. There's the platform itself is the ADRV9361 and then the ADRV9009, and that in itself is going to support new offerings by analog devices, as well as updating the matchstick. Right now we support the Z1, but they've made a lot of platforms since the last time we have any EPIC support it for EPIC platforms. For Intel support, Cyclone 5, Stratix 10, and then also refresh our GPU support to OpenCPL 3.0, and then interconnects like one that from the previous workshop was interested in seeing is a USB 3 for the B210 and 10 gigabit Ethernet, and then refreshing the PCI Express support as well. So to find more information, you can visit opencpi.org, and that contains general information. OpenCPI.gitlab.io, like I mentioned before, is the documentation. There's also tutorials and briefings if you want to learn more about OpenCPI. Our GitLab, where we store all our source code, our repository issues, where we have our CI system, and then our email discussion list as well. So this particular workshop will be, you can replay it at your convenience in the future, and also the introduction to OpenCPI with the GRC integration is available as well. I appreciate you guys joining me today on exploring platform development within OpenCPI. Thank the GNU Radio conference. Went really well, and I was glad to be able to be a part of it as well. Thank you. If you have any questions, feel free to chat with us, but we will be concluding this soon. You're welcome, Josh. Take care, guys.